Hi, just excuse me a minute while I go and get the subject of today's teardown. So this is a little pill camera designed to take photos of people's intestines and other insides to reach those places that a traditional gastroscope and endoscope can't quite reach. This was kindly donated by a relative who had this procedure done recently. This is a Myrocam model. This is different from some of the early devices in that instead of using radio transmission, it actually uses direct electrical conduction through the body using these two gold electrodes. These are picked up via some stick-on electrodes on the outside of the body that go to a little receiver unit. The electrodes are very similar to ECG type electrodes. One advantage of this is that it uses less power, so this thing can run for 12 hours, whereas earlier models could only do 8 hours. Which wasn't always enough to get through to all the bits of the intestines that the doctors wanted to look at. Another advantage is it makes the pill slightly smaller because there's no need for an RF transmitter and antenna in there. Here's a little demonstration of this body conduction principle. What I've got here is a piece of standard conductive foam. If we look at the resistance of that, that's about sort of a few hundred K over a short distance, which is of a similar sort of magnitude of the sort of conductivity of the fluids in the body. It's going to be in the sort of mid to high K sort of range, so it's fairly similar, and obviously the resistance is distributed throughout the material. So if we take this standard 9-volt battery and just plonk it in there to provide a voltage source. Now, because this is a resistive material, although quite a lot of the current will be flowing directly between the battery terminals, there will also be some additional current taking alternate paths, almost like the field lines of a bar magnet. So if we actually look at what we're seeing here, obviously very close to the battery we've got, so picking up sort of 70 millivolts. But as we move out, we've still got a reasonable voltage, so we're still picking up like 60 millivolts here. As we move out, yeah, pretty much anywhere around here, we're actually picking up the voltage from this battery, and if I actually push it in so it's making better contact, we'll probably get a bit more, yeah, about 100 millivolts or so. So that's only attenuating by, you know, of the order of maybe sort of 50 to 100. So if you imagine the pill's putting out maybe, I don't know, say a volt of signal, and you've got some reasonable amplification on the external electrodes, you've got a pretty decent amount of signal to deal with. It comes in this nice little plastic case. There's actually a silicone lens cap that I don't have that sits in here. There's a little silicone stopper. And there's these two contacts here. Now, took this apart and I found there's actually a battery in here. Now, my initial thoughts were, oh, maybe it's using this to charge the internal batteries, or maybe they're using a supercap or something. But I had a look under some of the patents assigned to this company, and what this actually is, this is simply providing a voltage to say, yeah, stay switched off, stay switched off. So instead of this thing actually having to use the voltage to internally to detect when the thing's taken out of the box, which will obviously use some of the internal battery, it just uses this extra battery to provide a continuous bias to turn it on. Sorry, to turn it on when the thing's removed from the case. So when it sees that voltage disappears, that's the signal for it to start working. And I mean, patents are actually quite a handy source of information if you're tearing down something you don't really know much about. You quite often find lots of, you know, quite interesting little snippets of information in there. And there's a little bump at the bottom there with possibly a bit of wire coming through it. This may be the connection to the outer electrode. I think this top one folds over the edge because you can actually see some gold inside through the lens. So I think this gold coating wraps around the top to get with that connection. This bottom connection I think is probably in this little dimple. Right, so I think let's see if we can crack this joint apart. Oh yeah, that was easy. Hope it doesn't come apart that easily when it's going through your digestive system. Right, so that's just the lens cap off. This outer shell looks like it's quite thin. It might be easy just to slit it down and cut it off. It looks like this top bit is springing up. I suspect there's probably some spring contacts on the batteries that are trying to push this up a little bit. I'm just going to try peeling this case off, I think, because I'd like to try and keep the innards intact. Right, we can see the batteries in here now. Right, and there we go. Right, so yeah, that in the bottom there looks like there's just some conductive paint that just goes through to the outside. So this is the actual insides. So the bottom, I'm not sure there's actually anything other than the contact. So that's the spring contact into the bottom. We've got a battery contact here, and there's this, the batteries are inside some heat shrink. Right, this all looks like it's all on a single piece of flex, which is not really surprising. There's the two battery contacts, they've sort of helpfully actually labelled them on there. And there's this bottom contact. I'm not sure if there's actually anything inside here at all, or if this is just a plastic spacer. There's some sort of plastic posts, I think that's for alignment, I suspect. I think it's actually glued onto the plastic. I'll leave that for the moment. I can't see if there's any circuitry inside this plastic piece or not. I've just peeled this bottom piece off. It's just stuck down, and so there's a sort of hollow section in the bottom, and there's just this resistor and a capacitor on there, one side of which will connect through to that bottom electrode, and you've got the battery terminal here and a bunch of test points. I'm guessing those are either manufacturing test or maybe even in circuit programming pads. And then we've got the rest of the assembly here. You've got the ring of leads, a bit of flex going up to the lead ring there. I don't think I'll try firing this up before I try to delve any further. And these are the contacts, spring contacts, to make contact with this top electrode here. That this metallization folds back. It's quite heavy. I don't know if it's a plating or a separate coating, but it's quite a thick coating. The batteries, there are a couple of silver oxide batteries. I'm guessing they use those because they've got provide a relatively high discharge current. Obviously these things are designed to last for about 12 hours and be sort of fully discharged within that period, so that's a much higher discharge rate than you get from a lithium. And it looks like they've got a little bit of conductive epoxy sticking the two cells together, because they've been heat shrunk. You could conceivably get some stresses built up that prevent the two centre batteries connecting if they were relying just on the pressure, so they've just put some silver epoxy on there. Just see what state these batteries are in. What's interesting is that one's showing 0.55 volts, but the other one is 1.3, so surprisingly unbalanced. You'd expect them both to be pretty much the same voltage, but it's a quite surprising difference there. Just see what sort of short circuit current we can get out of these in their current state. 10 milliamps or so, and 100 milliamps nearly. Just looked up the spec of these batteries. They're rated 1.55 volts at nominally 80 milliamp hours, so for a 12-hour life that's a nominal draw of about 6.5 milliamps. Okay, so let's give it some voltage, and away we go. Flashing away 3 milliamps. That's pretty impressive, taking 3 frames a second and transmitting that, all for 3 milliamps at 3 volts. That's pretty good. I think it's time to have a little poke around with the scope to see what this thing's actually spitting out. Obviously, as you'd expect, if we make it think it's in its little box with its little battery, it should switch off. Yeah, switches off and back on again. Right, this is showing a couple of waveforms. The top one is the waveform, the transmitted data waveform from the end electrode, and the bottom one is the LED enable. All 6 LEDs are connected in parallel. They're turned on for a 2 millisecond flash. There's no voltage boosting or anything, they just run off the main supply. The forward voltage of white LEDs does vary quite a lot, and I suspect what they probably do here to make sure they run okay on 3 volts is they select them, because you can get LEDs binned into different intensity grades and also different forward voltage grades. So I'd imagine for something like this they select them for good output at low voltage. One thing I did notice just now was it missed a flash. Now, looking through one of the patents, I think what it does is it does periodic dark frame subtraction, so every so often it'll send a frame with no illumination so that the receiver can then use that as a reference to subtract out any differences in pixel values due to fixed manufacturing differences in the sensor. Yeah, here you can see there's every so often it misses out a LED flash, so that's just sending a dark frame as a reference. Seems to do that about every 30 seconds or so. Right, let's take a look at this data packet, see if we can figure out what this thing's sending and what format it's sending in. Now, this is one of those applications that really separates the men from the boys when it comes from oscilloscopes. This is the sort of display you'd get in a sort of a cheap low-end storage scope. You just don't have the resolution. It's either, we've got quite a high density of data. Now, the first thing we want to do is get an overall picture. One thing I've done is I've set up a pulse width trigger, because the data's got this very obvious gap in it, so that's a nice easy place to trigger from. Most scopes nowadays have pulse width trigger, but the thing that really is the killer advantage when you're doing this is the intensity grading, which emulates the sort of functionality of an analog scope. And as I gradually decrease the intensity control, what you can now see is what the intensity is effectively a statistical representation of how long the data is at any particular point. So by tweaking the intensity, you can actually see different densities of data instantly, and there's just no way you'd be able to see this on a scope that didn't have this facility. So what we can see is we've got sort of two major sections here. We've got this section which looks like it's fair. We'll zoom in on this in a minute and take a closer look, but this is a preamble. So this is just a fixed carrier. This is about 1.5 megahertz. So this will be an initial signal for the receiver to lock onto. It's actually quite long. I'm surprised how long this preamble is. This might also be overlapping with some of the data transfer time from the camera to the device that's doing the sending. Yeah, a major function of this is going to be receiver synchronization. And so because of the intensity display, we can immediately see that there's different things going on here. The other really nice thing is deep memory, which means that you can just capture a single waveform and then zoom right in detail. And this has got 8 megapoints of memory. So when you've got a long and complex waveform, it means you can get a decent resolution, just capture it once and you zoom right into the detail. Obviously it starts getting a little bit crunchy when you get into extreme detail, and that's 100 nanoseconds per div. Whereas our main acquisition is 550 milliseconds, so we've got a huge amount of data to look at. The other handy thing is, if you've got a decent zoom facility, we can actually get both the overview and the detail here. So we can actually look at this sort of transition area here. Zoom in on this area. So there's clearly something going on here. If we zoom in on this data, so if we start off with the preamble, so this is our preamble data. What we then typically see, and this is a very common, you'll see this in a lot of things like RF communication systems. So the next thing we have after the preamble is a fixed synchronization pattern. So this is just an unchanging, so we're continuously acquiring here. This isn't a stop trace, so it's basically static data, and that's just a fixed pattern, so that once the receiver's locked onto the preamble, it can then actually get synchronized, because what you'll be sending is, you know, words of a number of bits at a time, so it needs to actually get the bit boundaries in the right place. Preamble, synchronization, and again the synchronization is quite long, but bear in mind this is trying to get a signal out of the human body from external electrodes, so I'm guessing they probably use quite a lot of processing in the receiver to actually extract reliable data. And now what we can see is what looks like a fairly regular pattern. So I'm guessing this is a frame number. You can actually see it's like a binary count. You've got stuff changing in a fairly regular pattern. I'm guessing this is a Manchester code or something very similar, in that you've only got 2 pulse widths. One reason for using Manchester code is that it's the average is 0, it hasn't got any DC offset, and when you're dealing in wet environments that's very important, because if you've got any DC you'll get electrolytic effects and corrosion and so on, but also from the point of view of receiving an AC signal, if there's no DC then it's much easier to actually extract the data, because you don't have to worry about offsets. You can just take the average as your reference line to then slice the data into highs and lows, and you can actually see the output for this thing is actually bipolar. This is our ground level here, so the thing is swinging above and below ground. The actual amplitude on that's about 1 volt per div, so it's going about 1.5 volts either side of ground onto the patient electrode. So yeah, so this looks like a header. We've got what's clearly some sort of frame count. There's probably also going to be a unique ID on this. I mean, on the packet there's a serial number that they tear off and put with the patient information, so my guess is that this thing transmits a unique ID, so they're absolutely sure that they know which patient's data they're looking at when they're looking at the download log. And what we've got here, we've got a fairly regular structure here, which I'm guessing each one of these is one line of data. So what I'm going to do, I'm just going to put a very high contrasty target in front of the camera to see if we can see any changes happening there. Well, one problem with Manchester code, because it's DC free, it can be quite hard to actually see changes in data, but so if you tweak the intensity control you can usually get enough to see something going on. And if we actually zoom out and look at the timing, we can actually see this regular line structure. And from the online specs I found, I know this sensor is 320 by 320 pixels, and if we time that, my guess is we'll find that that corresponds to one line, so probably from there till yes, about 900 microseconds, which so 320 corresponds to our roughly 3 frames per second. As you can actually see the image data fairly clearly in here. It looks like there's no compression. This is a whole frame of data. I'm not too surprised that it's uncompressed. You might think, oh well, why not use JPEG or something, because you've got a limited transmission bandwidth, but the problem is things like JPEG need quite a lot of power and silicon area to do, so obviously both power and area are very constrained in a device like this, so just to keep the camera as simple as possible, it's just sending uncompressed frames. It probably wouldn't actually be too hard to figure out and decode this. It's probably literally Manchester code. You'd need to figure out how many bits per pixel there were, which you could do that from the timing quite easily, I think. I'm just shining a light directly into the camera. It's actually easier to produce a nice contrasty image. So this is showing one line. If I just slide my finger in front of the light, you can very clearly see the pattern. I'm just trying to figure out how many bits per pixel this thing's sending. Let me just grab one data. So the Manchester code, basically the bits are encoded as either with a fixed cell timing, there's either no transition in a cell or there's a transmission in the middle of the cell, and there's always a transmission at the end. This is exactly the same coding that's used for RC5 remote controls as well. So we've got a bit cell there, one there with a transition, one there with no transition, one there with no transition. So from this we know that the actual bit time is around 360 nanoseconds. And just looking at the overall structure of the data, the line time is about 900 microseconds. So that gives about 2,500 bits per line, divided by 320 comes to 7.8. So yeah, and it's probably almost certainly 8 bits per pixel. Look at the overall structure of this. So the flex comes in here, there's probably parts underneath here, it then folds round, then across, and then the last bit folds up just for the lead ring. So I think, see if we can unfold this a little bit. Right, I've undone this first fold. Couldn't really do this on camera. I had to use my Mantis magnifier because it's just so hard to see. I didn't want to risk breaking anything. First surprise, there's a crystal in there. Now, the whole point about Manchester code is it's self-clocking, so I'm just a little bit surprised that they actually used a crystal rather than an RC oscillator, because the receiver ought to be able to track any small changes in frequency, and considering how space constrained these things are, a little bit surprised. Well, having said that, I mean, I did see in one of the specs somewhere for this product they reckon they've got 10% free space inside here for future expansion, and so there is a little bit of space here in the cavity under this bottom spacer. And so there's not a lot of room here. You've got just this cavity and a few passives here that will go up to the layer that's got the, what I'm guessing is probably just literally a single chip CMOS sensor and encoder. Right, we're just taking that plastic spacer off, and the flex here becomes a flex rigid assembly. Obviously they probably need a few more layers. I don't think it's possible to get more than 2 layers on flex. I don't think I've ever seen a multi-layer flex. So this actually seems to go onto a slightly more rigid PCB. There's a few passives mounted there. In fact, from the back you can see a sort of BGA footprint in there, which will be the image sensor itself. Right, unfortunately I damaged the lead ring getting that off, because the glue they'd used to lock the lens had got under it, and that was a much tougher glue than what was used to hold everything else, but one, the lead still flashes. That is the first element of the lens. It's actually quite a wide angle. It's something like, oh, well, that was it. It's about 150 degree angle of view, and then there's a second element in here. Right, with that second lens element out, you can actually now see the image sensor. And this is going to be pretty much the same sort of sensor that you see in like mobile phones and the like, except there probably won't be an infrared cut filter on it, because of course the only light source is the white LED, so it will just have an RGB filter on there. And it looks like all the encoding for their transmission system is integrated on chip. There aren't any other chips in there. So it may well be they've taken a standard image sensor, CMOS image sensor, and then customized it with their encoder. Right, it's managed to peel off the rest of the lens assembly. And yeah, all that's in there, there's one other chip in there which I'm guessing is a voltage regulator, judging by the number of pins, and the image sensor. I might just be able to see the solder balls. It's a BGA package. And so this is a flex rigid assembly, which is a fairly standard technique for high density circuits. So yeah, the flex effectively form, you've got a sort of standard PCB, but the flex is actually laminated to form part of that PCB. So they've used that because of the extra layers they need to deal with the BGA. Maybe also for the rigidity to hold the sensor in at an accurate distance to the lens through the lens housing. And there's just a few passives around there, not much else in there. And it is still working, albeit with only one LED. Right, before this thing goes back to the hospital, I think we should have a little look at the receiver. It's in a sort of zip case so the patient can carry it around. It's got a shoulder strap. There's a compartment here to take any surplus cables. It's just a sort of fairly nicely made sort of pouch thing. Little Myrocam thing there. So this is the actual receiver unit. The electrodes are pretty much identical to ECG electrodes. They're a disposable electrode with a press stud, conductive gel pad. They go into this doubtless very expensive multi-pin connector with a just a retaining clip, so that plugs into there. Again, multi-pin connector there. It just clicks in there. I'm not actually sure what the purpose of this is. It doesn't actually seem to clip to anything. I don't know if there's anything in there, and this is completely moulded, so I doubt there's any electronics in there. There's this lump of ferrite obviously for shielding, because these things are going to act as antennas if someone's walking around using mobile phone and whatever. It's obviously going to induce some current into these probe leads. I'd imagine these are probably shielded. So this is the main receiver unit. They've even left the, I hate it when people leave the plastic on things. I think that's going to have to go. It's a very sort of modern iPhone style, sort of shiny plastic, modern consumer electronics type construction. On the side there's just an on-off switch, simple slide on-off switch, and here we've got a standard mini USB connection. Switch on, just turn it on, get some bleeps, LEDs light up. There's three LEDs here. SIG means signal, that lights up, that changes to green when it gets a signal from the camera when it's connected to the patient. INI, that means that it needs initializing. That means basically it's got data in it and it needs that data downloading and resetting before it can do another log operation. And battery, obviously this has been run, so it's showing a low battery indication. It's a fairly big battery. Obviously this thing's going to run for about 12 hours logging data, receiving and writing data continuously, so the power consumption is not insignificant, and this whole thing does actually get noticeably warm after a full run. Battery just unclips on the back. Let's see, it's a 3.7 volt lithium ion, 10 amp hours, so it's a 38 watt hour battery, so it's a fair old amount of capacity, and obviously these are designed to do a single run and then be downloaded. Right, so this is what's inside this receiver. Single PCB. One thing notice here, there's quite a few cuts in the PCB with these big capacitors going across. Now I'm guessing this is the medical isolation barrier, because although this is a battery powered piece of kit, you can plug the USB in and to get live pictures, and because the electrodes are connected to the patient, you can't, obviously you might have a problem with your PC suddenly decides to put the mains up its USB port. You really don't want that to go anywhere near the patient, so pretty much any bit of medical equipment will have some fairly serious isolation between anything external and any patient connected electrodes. So we've got a cut in the PCB spanned by these large capacitors, so this is probably going to be just like a capacitive coupling barrier. That I'm guessing is either an opto isolator or possibly a small DC to DC converter to give power for the isolated side. Up here we've got a net chip. I think that's a USB interface by the looks of it. That is, I think, flash or possibly SRAM. There's a big Texas Instruments DSP, which is the main processor, and there's a Xilinx FPGA down here. Crystal for clock generation. That would be the Xilinx configuration PROM. That I'm sure will be the A to D converter. You can actually see the sort of a separate ground, and the converter's bridging the ground lines. What else we've got in here? Actually, that one's also got a Xilinx. Maybe not. I think that's probably the Xilinx config prob. That's also got a Xilinx on it. Maybe that's a CPLD or something. I can't quite read the number. There's some ink over the top of it. Couple of NAND flash chips, which is the main data storage. And the other side of the PCB, not a great deal more. We've got more of these isolation caps. I think literally these electrodes are literally simply connected by series capacitors, because this is going to be looking for an AC signal from the camera. Or what they're doing, I think, is just a fairly simple AC coupling deal on that. And there's a chip there that's going to be a front end chip or something. There's a little fuse up there and a couple more flash memory chips, and not really a great deal else. Not quite sure what the deal is with this extra little wire that seems to go to the connector, unless maybe that's a shield or something. There's you see there's also some more another ferrite on the back of that connector there, a little ferrite ring here into the connector, and there's also a little programming connector there. So that was a fascinating little bit of technology. The real surprise was that it was this body conduction technique thing, which I really didn't know about until I actually found the brand name and had a look at that. Quick bit of searching on the net, these things look like they're about $700 US each, which is obviously a huge amount of money for what's in it, but obviously there's a huge amount of investment in the custom sensor and medical approvals and the fact that anything medical is expensive anyway. I'd quite like to look at some of the other types of cameras, so if you know of anyone having a procedure and you're prepared to do the recovery, I'll be most happy to pay postage to have a look at a different one of these, but please clean it first.